Here's something. I'm gonna explain that here in a minute.
Okay. I think I'm gonna keep that one for this on here because I haven't figured
Okay. Gotcha. Okay, well, what I'm gonna be doing is I'm gonna be lecturing. So I'll be posting just like I will with class. I'll post I'll watch that. Okay, folks, let me get the sign-in sheet going around. Make sure everybody gets to sign it, please. Okay. So I just wanted to take a few minutes to do a few of the highlights. As per normal, active homework is, I mean, you basically have from the last class till the next class, the night before the next class. Now, you'll notice that most of them have this adaptive follow-up. The adaptive follow-up, and I had to wait and see how things work. The adaptive follow-up actually does not impact your grade. But what it is there for is if you do poorly on the homework, you have an opportunity to try some more problems and see if you can't, see if it gets better. So that's the adaptive follow-up. The other thing on active is you do have, I believe it's quiz number 2 due tonight at 11:59 p.m. So that is just the stuff on active. Any questions? Blackboard. Now with Blackboard, now that we've been at this for 3 weeks, I think that's all. I wanted to take a moment and just ask you questions. Number 1, is the setup working? You can read it. You can then click on the folder and find the subfolders. That is how I try to do everything. And this week is a better example of how it's going to come out before at a much earlier time. So it should be complete. So hopefully that helped a lot with making sure you got everything done, because you could go through that checklist of what was due that week, check it off, what was due the next week and check it off. So hopefully that's helping out. Anything I need to change on Blackboard that you think would be beneficial to the class? Okay, because I'm willing to listen, and if I thought it would work. So if you do come up with something that I'm not doing, let me know. But I am trying my best to get everything up on Blackboard in one location. So, okay. The next thing is lab. If you read the folder for this week, you'll realize we're not doing an actual lab. It is a lab lecture. So come prepared to take more notes. We will still meet in the lab. Now, when I do a lab lecture, the way it normally works is I'll go for about an hour. We'll take a 10-minute break and then we'll go for another bit. So I do try to let you get up and move around in between. Now, as far as food, drink and stuff, lab lectures, the only time I will allow a drink in there, but it must have a closed top. In other words, it can't be an open can. It has to be a bottle. Something that you can close. That way, if it gets knocked over, it does not make a mess. But I will allow drinks. I still will not allow food. No food in the lab. But I will allow a drink during lecture. Any questions about that? The other thing I just, even though I did not put it on here, the other thing I wanted to make you aware of is if you looked at this week's folder, one of the things you'll notice is next week is your first exam. And I listed the topics that I expect to be on that exam. So. Any questions for me? And no, I don't do a study guide for an exam. That's where the optional homework comes in really, really handy. Because the optional homework looks a lot like past exam problems. So. Okay, so my goal today is we are going to pick up where we left off on Thursday. On Thursday, I introduced the proton, the neutron, and the electron, which are the three subatomic particles in an atom of an element. The proton and the neutron are found within the nucleus. The electrons are found in the electron cloud. The protons determine the identity of the element. The neutrons determine the isotope of the element, and the electrons are responsible for an element's reactivity. Protons carry with them a +1 charge. The electrons carry with them a -1 charge, and a neutron is no charge. Now, two other terms that were introduced were the atomic number and the mass number. The atomic number is found on the periodic table. Hydrogen is element number 1. Well, that 1 is actually its atomic number. Mercury is element number 80 on the periodic table. Well, that 80 is actually its atomic number. And then the mass number is equal to the number of protons plus the number of neutrons. Now, folks, on a set of problems, I'm either going to have to give you the number of neutrons or I'm going to have to give you the mass number in some shape, form, or fashion. You cannot possibly know the mass number simply by looking at the periodic table because it is not on the periodic table. The mass number is a whole number. It is always a whole number because you can't have a partial proton. You can't have a partial neutron. So the mass number is always a whole number, and it is not found on the periodic table because it depends upon the naturally occurring isotope. So we're going to be looking at determining the atomic number, mass number, protons, neutrons, electrons for a variety of elements. Then we're going to, talk, before we get to that, we'll talk about the isotopic symbol. There are 3 ways that we indicate an isotope of an element, and that would be considered the isotopic symbol. Then we'll talk about, after we completely do some problems on that, then we're going to get into the average atomic mass, calculation of the average atomic mass, and then finally, if time permits, we will start our conversation on the nature of light, because it is actually because of the nature of light that we started to understand the electron cloud. So, okay. So the first thing I'm really wanting to do is get into this isotopic symbol. Now, the first isotopic symbol would have X, where we're going to call X is equal to our element. As a superscript to the left, you will have the mass number. And as a subscript to the left, you would have the atomic number. Okay, so yes, we went through this. I'm going to just go back through it because this is where we're headed. But you're right, I forgot. That's where I ended. Thank you. And so we talked about the fact that if you look at these 2 factors, they are duplicates. Basically, they're just reiterating the same thing. So then you can just do the mass number, and you can write it as the element symbol to the mass number, or you can write it as the elemental symbol dash mass number. But either way, you're gonna get the mass number or you're gonna get the number of neutrons. So let's look at how all of this would be arranged. It will come in the form of a table. Now, let's see. Okay, we will do. Let's go with that. You'd be asked to fill in this table. So with the first one, the thing I see is, okay, I'm dealing with lithium. I look at the periodic table. Lithium is element number 3. So it would have a atomic number of 3. The atomic number is equal to the number of protons, and in a neutral atom equal to the number of electrons. Remembering that the mass number is equal to the number of protons plus the number of neutrons. That means that this is going to have a mass number of 6. So this would be lithium 6. So no, not all elements do have an isotope. There are some that only have one isotope of the element. I mean, they all have at least one, but there are, most of them have more than one. Okay, so in the next one, I look at the atomic number and I see it's a 10. So I go find element 10 on the periodic table, and that is going to be neon. Because the top number is the atomic number. The atomic number is the same as the number of protons and the number of electrons in a neutral atom. You can use your mass number to get down to the number of neutrons, because if you were to think about it, then it would be 21 is equal to 10 plus the number of neutrons. And so you can do the math and you would get 11 neutrons. So this would be neon 21. I want you to do the last three, and then I'll come in and give you answers. $62. Nickel 62. Okay, I'm going to wake you up. This is about to become interactive here. So, row 3, the element is nickel. Oh, come on, be nice. What is the number of protons? 28, because it is element number 28, which would be its atomic number. So what else is 28? The electrons. Now, what is its mass number, A? 62, and that means that the number of neutrons is. Let's go to the next one. What is the element? Zinc, and how did I know? Huh? The protons is equal to what? The atomic number. So it had to be zinc. What else is equal to 30? Because in a neutral atom, they're all the same. So what is the mass number for this zinc? This thing sometimes acts funky. I think I've used it too much. 68. So what should I write as the isotope symbol? ZN-68 works. Any questions so far? Folks, now's a great time to speak up because it's on the homework and it'll be on the test and stuff like that. Okay, moving on to the last one. What element am I working with? Strontium? How did I know that? The electrons are equal to what? The protons, and the protons are equal to what? The atomic number, which is what is on the periodic table. And what is its mass number? So this would be strontium 84. Questions? If I were to give you, let me think. If I were to give you something like this, first of all, which two represent isotopes? I think I heard second and third, first and last. Who thinks it's first and last? Who thinks it's second and third? Who's hesitant to answer? Okay. The answer is the first and third. Why? They have the same atomic number. which is what identifies the element. So what element is this, by the way? This is rubidium. Questions about that question? Because most likely you'll see something like that too. You got to look at the atomic number. The atomic number is the key to identifying whether it's the same element. And the term isotope refers to it being the same element, just different mass numbers. Yes, early in the semester, I gave you a copy of a periodic table that was completely filled in. That's the same periodic table you will receive on each exam. It'll be stapled to the back of the exam along with a formula sheet. Okay. Any questions about the first two topics of today? Then we move on to the next topic. So I've said multiple times, the mass number's not on the periodic table. What is shown on the periodic table is the average atomic mass. The average atomic mass takes into account all naturally occurring isotopes and their abundances. You are being very stubborn today. You can calculate the average atomic mass it is equal to the sum over all naturally occurring isotopes of the isotope mass times the abundance. Again, even though it doesn't look like it, it's supposed to be a capital sigma. And it means sum, so addition. Okay, so let's look at some examples and I'll walk through this process. Now let's go with the rubidium again. Okay. So when I look at rubidium, and folks, I don't even know all the isotopes. I have to look them up. It's not something that you just know. It is something that has to be looked up. Now, what I will say, when we get this average atomic mass, it's probably going to be really close, but it may not be exactly that number, because it all depends upon what table the folks that made that periodic table went to. And the reason that these masses vary slightly is because, if you'll recall, when we were talking about a proton, it came out to be 1.0079 something AMUs for one proton. Well, each of those protons in helium, there's two protons. The first proton brings it with it 1.0079 something. The next proton brings with it 1.0079 something. One of the common isotopes of helium is helium-4. So not only do you have the two protons, but you have two neutrons, this one bringing 1.00866, this one bringing 1.00866. And then you have the two electrons, one bringing 0.00055, the other one bringing 0.00055. But those numbers even are averages. So what I'm trying to say is, once you get into these tables, what they've done is they've given you an average mass for that particular isotope. But depending upon which table I go to, it might be tweaked only slightly. And I'm talking very slightly. So when we finish these calculations, we'll come pretty close to those numbers, but they may not be exact down to the decimal that's there, but it'll be close. So let's look at rubidium. So there are two rubidium isotopes. There is rubidium 85 and there is rubidium 87. Rubidium 85, according to the table I have, has a mass of 84.911789 AMUs. And it is present 72.17% of the time. Rubidium 87 is 86.909183, and it is present 27.83% of the time. Now, if you look at the formula I gave you a minute ago, I said it was the mass times the abundance, not the percent abundance. So you need to take your numbers out of percentages. By dividing by 100. Now we can use our equation. Average atomic mass is going to be equal to the mass of the isotope. So let's go with 85. So that would be 84.911789 times its abundance of 0.7217 plus the mass of the other isotope, 87, which is 86.909183 times its abundance of 0.2783. You get 61.280838, and it can continue. For the first one. For the second one. You get 24.186826. You add those two together. And you get a total of 85.46766 AMUs. If you look over at the periodic table, rubidium is 85.4678. That's where the number came from. It's from its two naturally occurring isotopes and their abundances. Yes.
What is the importance of isotopes? Like, why would we need to know that different elements have isotopes?
So there are a lot of uses for isotopes. For instance, some isotopes are used medically, whereas the other isotopes of an element are not, because they're radioactive or they give off a certain characteristic. When you get to organic chemistry, one of the things you're going to learn is nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy, there are two types that you'll use. There's proton, and then there is one that's related to carbon. Now, when we talk about the one that's related to the proton, we're talking H1. But when you do a carbon one, you're talking about carbon-13. So we can actually use certain isotopes in our substances because of a certain characteristic. So that's why the isotopes actually do matter. Now, that means also, when I go dig up, for instance, if I only wanted rubidium-87, when I go dig up a sample of rubidium, I have to separate the two isotopes and then just use this one. So understanding the abundance also comes into play, because that'll help us in understanding about how much material we need to get a particular isotope. Does that answer your question? Any other questions? But that's why isotopes can be of importance. Did we worry about it too much in college camp? No. But they do have their importance, and so knowing they're out there is important. Okay, let me give you one to do real quick, and then we'll be moving on from this. So, come on, wake up. There you go. Figure out the average atomic mass for silicon. See if I can move this up where you can see better. Okay, when you calculated it, first of all, I took the percent abundances divided by 100 to get the abundance. And then I performed the mathematics. I calculated 28.08541. And if I look at the periodic table, it has it listed as 28.0855. That's what I meant earlier. This little bitty difference here that occurs due to this little bitty difference is due to the fact that I used this table and they probably used a different table. But it should not be a big difference. It's going to come out to be a small difference between what's on our table and what you can calculate. Now, what that means though, folks, is I do require you to show your work. Just to let you know. I am okay as long as I see the change to the abundance, and then you can, I'm gonna guess that you knew what you were doing, because this is basically what you see here is what you're gonna get on the test. So. On this problem, no. If I did worry about sig figs, I would get that answer to the exact number because of the where the rounding would have occurred. But I do not make you do it on this problem. Questions about this? So now, hopefully, yes, you know mass number and average atomic mass are different. Up there is average atomic mass. Mass number's not up there. So, any questions before I move on? Okay, I will forewarn you for the next couple of class periods. You're probably going to be, I mean, as we go through this first part, the math is going to be the key. But as far as getting into understanding what all the math means, I will warn you that the next 2 or 3 classes may be, and then hopefully once we start really getting into electron configurations and stuff like that, everything will start to coalesce again. So I'm forewarning you that there's a lot of information that I'm about to dish out that went into understanding the electron configurations. But until we really get into those electron configurations and looking and doing some comparisons from the electron configuration back to what I'm going to discuss, it may be a little bit of a, maybe a little shaky. So don't panic is all I'm getting at. So what we are about to get into is the nature of light. The reason we get into the nature of light is because observations related to light were our first indication of how the electrons in an atom behave. We're going to talk about some of the observations that led to our current understanding of electron configurations. Those observations are going to include the photoelectric effect. Those observations are going to include the electromagnetic spectrum for an atom of an element, or the atomic spectrum, as we refer to it. And as we progress, initially I'm going to throw out the concepts, but then we're going to use as our first basic understanding, we're going to use the Bohr model to try to really pick apart why. Then as we continue to progress, we're going to find out the Bohr model only works for hydrogen. And we really start getting into a better understanding of our electron configurations when we start getting into quantum mechanics. So now, don't panic. We'll stick to algebra. Even though the mathematics behind our understanding of electron configuration requires calculus, specifically Cal 2 integrals. I'm not going to go there. I'm going to stick to the algebra and do a little bit of one magic when we get to that point to jump, because I'm not going to expect you to solve for it. And the reason I don't expect you to solve for it is, even as a graduate student, I can solve for hydrogen, but it takes a long time to even solve for helium. Once you start getting further and further down the periodic table, it takes supercomputers to solve it in a reasonable amount of time. So that's why we're going to do a little bit of magic and go on. But okay, the nature of light. First of all, light can be described by amplitude, which is the size of the wave, it can be described by the wavelength, which is the distance between adjacent troughs. I'll show you in a minute. Or adjacent peaks. And by the frequency. Which is the number of waves that pass a given point in a certain amount of time. Now, as far as these units are concerned, distance is the key here for the wavelengths. And, or the term length. So the most common units we're going to be using are going to be meter and nanometer, though it can be any form of length. Those are just the most common. As far as frequency is concerned, we'll use the number of waves per second. Now, this can be written in a couple of different ways. You'll also see it written as number of waves second minus 1, because anything that has a negative exponent means that it's in the denominator. Or hertz. They all mean the same thing. These are just different ways to express a certain number of waves per second. This one, oh, that's the nu. That's Greek letter nu. So the Greek letter lambda and the Greek letter nu. Okay, so let's talk about these different things. The first one we'll talk about is going to be the amplitude. So when I talk about the amplitude, I'm talking about the size of the peak. This is the amplitude. Now, folks, you actually have experience with amplitude, even if you don't know it. When you buy a flashlight and it has fresh bulbs, it's very bright. That means it has a large amplitude. But towards the end of the battery's life, or the bulb's life, but one of the two, it becomes very weak light. And you're like, I can't even see with this stupid flashlight. That means that it would have a low amplitude. Questions about amplitude? Amplitude is going to come into a tiny fraction of play when we start talking about the photoelectric effect, because we're going to talk about what they did not expect. And what they didn't expect has to do with the amplitude. So now, wavelength. So the wavelength is either the distance between the peaks, or it is the distance between the troughs. And even though I did a bad job, that is what we're looking at. Then we have frequency. And remember, it's the number of waves per given amount of time. So the top one has a high frequency. And the bottom one has a low frequency. Because we're looking at the number of waves that pass a specific point at any given time. Now, what do you notice about wavelength and frequency? Comparability, comparing it. Looking at this particular picture that's on the screen, what can you say about wavelength and frequency? High frequency means short wavelengths. Low frequency means long wavelengths. So in other words, they're inversely related. Now, we can move between frequency and wavelength, or wavelength and frequency, using the equation for the speed of light. The speed of light is represented with a lowercase c. And it is the constant 2.998 times 10 to the 8 meters per second. Now, this relationship is that the speed of light is equal to the frequency times the wavelength. The equation's quite simple, folks. So what is the trick to this equation? The trick to the equation is that the speed of light is dictating the units for wavelength and frequency. So let's see what I mean. What is the frequency of light that has a wavelength of 480 nanometers. So the first thing I see is what is the frequency? That means that I am wanting to calculate nu. I am given the wavelength of 480 nanometers. When I see frequency and wavelength, and that's all I see, frequency and wavelength, then that is your cue that you're going to be using your speed of light equation. If you see nothing but frequency and wavelength, you've got to use the speed of light equation. Therefore, you're going to need the speed of light, which is the constant 2.998 times 10 to the 8 meters per second. Now, here's where I was talking about the fact that your speed of light dictates the unit. The speed of light is telling you that the unit must be in meters to be able to use the equation. So you're going to need to be prepared to convert those nanometers to meters. (480 nanometers). There is 1 times 10 to the minus 9 meters per 1 nanometer. That is one of your prefix unit conversions. So when you complete this calculation, you get 4.80 times 10 to the negative 7 meters. One thing you're going to hear me say a lot is if you have a constant, make every unit match your constant. Always make every unit match your constant. If you got a constant, just make all the units match it. You're going to hear that from now until the end of the semester. Every time I've got a constant, I'm going to make my units match the constant because my constant's dictating what the unit should be. So now I have my numbers. I'm going to rearrange this equation to solve for the frequency by dividing both sides through by the wavelength. So C over the wavelength is equal to the frequency. Because I've already made my units match, it is a matter of plugging in my numbers. Into my calculation, and I get a frequency of, this is always the more challenging ones to do on the phone. It comes out to be equal to 6.25 times 10 to the 14 per second. One thing I will tell you to help you out a little bit, just a note. If it is visible light, the wavelength will be to 10 to the -7 meters. The frequency will be to 10 to the negative, or 10 to the 14, excuse me, 14 per second. And when we talk about it on Thursday, the energy will be to 10 to the -19 joules. I can't say that's true for ultraviolet light or infrared, because to be quite honest, visible light is a very tiny fraction of the overall electromagnetic spectrum. And once you go below it or above it, you're gonna have some that fall into the same category, but some that'll be a different, slightly different number. So, but for your visible light, if it is a color you can see, this is the information that it should come to. So if you don't get that, you have keyed it into your calculator incorrectly if it is visible light. Questions? Okay, so we'll pick up with one of these problems on Thursday, and then we're going to talk about the photoelectric effect, and then energy, and then we're going to get into the atomic spectra, and then we'll start getting into the Bohr model and stuff. Make sure you sign the sign-in sheet wherever it went.